Hello and welcome back to the Juniper JNCIS Enterprise Routing and Switching Training Series. In this section, we will be talking about IP tunneling. We will be discussing IP/IP and GRE tunnels, but we will not be covering IPsec in this section. We will talk about the concepts, requirements, and functionality of these types of IP tunnels. Remember, if you need to watch a section twice, please do so and take notes as you go. An IP tunnel is used to connect two different geographical locations with the use of native routing paths between one another. IP tunnels can be created by encapsulating the IP packet with a header. In its most basic form, an IP tunnel is a communications channel between two different networks. The networks joined by an IP tunnel are often geographically dispersed and have no native routing path between one another. Because no native routing paths exist between the remote networks, a transport network, such as the Internet, is required to allow the tunnel to form and IP communications to occur. IP tunnels require a tunneling protocol, which can provide secure or unsecure communications, depending on the protocol selected. Tunneling protocols can use data encryption to transport insecure payload protocols over a public network, such as the Internet, thereby providing VPN functionality. IP security, or IPsec, has an end-to-end transport mode, but can also operate in a tunneling mode through a trusted security gateway. We cover IPsec in detail in other training courses. In this chapter, we highlight GRE and IP/IP, which are insecure tunneling protocols. Generic Routing Encapsulation, or GRE, uses encapsulation and decapsulation of IP packets with attachment and detachment of GRE headers. The config is done on a source and destination basis. It is a 24-byte header. The protocol is used to tunnel IP as well as non-IP packets, such as IPX and AppleTalk. Encapsulation. When a switch receives a data packet to be tunneled, it sends the packet to a tunnel interface. The tunnel interface encapsulates the data in a GRE packet. The system encapsulates the GRE packet into an IP packet. The IP packet is forwarded based on its destination address and routing table. Decapsulation. When the destination switch receives the IP packet from the tunnel interface, the switch checks the destination address. The IP header is removed and the packet is submitted to the GRE protocol. The GRE protocol strips off the GRE header and submits the payload packet for forwarding. GRE packets that are encapsulated in IP packets use IP protocol type 47. This is to ensure the inner IP packet is never modified except the TTL field. The TTL field must be decremented to ensure that the packet does not live forever. GRE packets that are encapsulated in IP packets use IP protocol type 47. Here is an example of a configuration output that shows a GRE tunnel interface as well as the static routing options to go with the tunnel. Let's talk a minute about IP/IP. There is no difference between the GRE and IP/IP protocols except that IP/IP is used only for IP packets. The mechanism works the same as GRE. There are few routing requirements for tunneling, including endpoints should have the valid route for tunneling, endpoints should have the proper route to direct traffic into the tunnel, intermediate devices should have valid routes to the endpoints. Tunnel specifications. GRE and IP/IP tunnels are completely stateless, which means that the tunnel endpoints do not know about the state or availability of the remote tunnel endpoint. The local tunnel endpoint does not have the ability to bring the GRE tunnel interface down if the remote endpoint is unreachable. The inability to mark an interface down when the remote tunnel endpoint is unavailable means that any associated routes dependent on that interface, such as static routes, remain in the routing table, whether or not the tunnel is actually usable. There are multiple case studies located in the Juniper exam prep material for IP tunneling, and you should take some time to read through them. In the meantime, we are going to move on to the next section. Let's take a look at an excerpt from the Juniper JNCIS ENT Study Material Guide from Chapter 5, Section 5. As we mentioned before, by default, GRE and IP tunnels are completely stateless, which means the tunnel endpoints do not know the state or availability of the remote tunnel endpoint. Because of this, the local tunnel endpoint does not have the ability to bring the GRE tunnel interface down if the remote endpoint is unreachable. The inability to mark the interface down when the remote tunnel endpoint is unavailable means that any associated routes depending on the interface remain in the routing table whether or not the tunnel is actually usable. The described behavior can cause problems in certain situations. Some implementations of GRE support a keep alive mechanism to monitor the health and availability of the tunnel endpoints. Using keep alives to monitor the tunnel can greatly reduce the potential risk of sending traffic through a stateless tunnel. The following is a configuration example of a GRE keep alive configuration. When configuring the keep alive, you must specify the family INET statement in the Edit Interfaces, Interface-Name, Unit configuration hierarchy level. The hold time must also be twice the keep alive time. GRE keep alives are supported on the M series and MX series devices. You can also use bidirectional forwarding detection, or BFD, in conjunction with your GRE tunnels to help accomplish the same basic functionality. We cover BFD in more detail in the high availability chapter. The IP protocol was designed to be used over a variety of interface types. Although the maximum length of an IP packet is 64 kilobytes, most interface types enforce a significantly smaller maximum packet size, known as a maximum transmission unit, or MTU. The MTU used depends on the interface type. The IP protocol accommodates different MTU values by allowing routers to fragment IP packets as necessary. The host receiving fragmented packets is responsible for reassembling the fragments back into their original packet. IP fragmentation involves breaking a packet into several pieces that can later be reassembled. The IP source, destination, identification, total length, and fragment offset fields, along with the more fragments and don't fragments flag in the IP header, are used for IP fragmentation and reassembly. When two devices communicate using TCP, they determine the maximum segment size, or MSS, permitted over the end-to-end communication path. Typically, the MSS turns out to be 1500 bytes, which is the maximum amount of payload in the Ethernet frame. This approach works well until overhead is added somewhere between the communicating devices, like in the case of IP and GRE tunnels, where additional headers are added. When packets transverse a GRE tunnel, for example, the maximum packet size is reduced from 1500 to 1476 to account for the additional overhead of 24 bytes. 4 bytes for the GRE header plus 20 bytes for the IP header. In a situation like this, if either host sends a packet that is larger than 1476, the packet must be fragmented, typically by one of the tunnel endpoints, to cross the tunnel. Unfortunately, the hosts do not realize this fact, because they only communicate with one another and agree upon the 1500 value. Each tunnel endpoint must have a valid route to the remote tunnel endpoint. For proper tunnel operation, this route must resolve to the physical next hop in the end-to-end communication path, and should never use a recursive route, which is a route for which the best path to the remote tunnel endpoint is through the tunnel itself. If a tunnel endpoint uses the tunnel as the best path to the remote tunnel endpoint, the tunnel interface bounces and becomes unusable. We recommend that you configure static routes. Juniper recommends you configure static routes on the tunnel endpoints for the destination tunnel endpoint to avoid problems like these. Okay, so let's review. What are some common reasons to use IP tunnels? Although there might be many reasons to use IP tunnels, we're going to mention a few common scenarios in which they're used. IP tunnels are used to carry traffic that otherwise is not routable over a public network like the Internet. The traffic could include IPX, AppleTalk, or IP traffic that uses RFC 1918 addressing. You can also use IP tunnels as a backup link in case failure occurs. Let's name some differences between GRE and IP-IP tunnels. Some differences between GRE and IP-IP include the encapsulation format used by each tunneling protocol and the types of protocols each protocol can encapsulate. IP-IP adds an additional IP header to the payload packet, whereas GRE adds a GRE header as well as an outer IP header. IP-IP encapsulates an IP packet, whereas GRE can encapsulate a number of network layer protocols such as IPX, AppleTalk, and IP. What are some key requirements of GRE and IP-IP tunnels? Well, both IP-IP and GRE tunnels require tunnel interfaces and end-to-end communication paths with the required routing information on all participating routers. Why should the route for a remote tunnel endpoint be specific and use a low route preference? The route to the remote tunnel endpoint should be specific and use a low route preference to ensure tunnel stability. If a more preferred route to the remote tunnel endpoint is received over the tunnel interface will go down. And that's it for IP tunneling. Now it's time to take the quiz and move on to the next section. Thanks for watching.